Hello, my name is Martin Ottinger. I'm the Senior Advisor for Carbon Capture and Transport within the Global CCS Institute, and I'm a member of the Institute's project team liaising with CCS projects around the world. I'd like to welcome our international audience. We have attendees from around the globe. This webinar is being recorded and will be made available on our website in the near future. We welcome questions asked throughout this presentation. These will be moderated and presented to American Electric Power. The topic we'll be discussing today is American Electric Power's FEED study on their CCS project at the Mountaineer plant in New Haven, West Virginia. There's been considerable interest in this project, and we're grateful that AEP are here to share their findings on this FEED study with us. AEP have recently completed a number of technical reports for the Institute on the integration task for the plant, a compressor evaluation study, and a storage report, all of which are available on the Global CCS Institute's website. The FEED studies report is being finalised and is likely to be available in January of 2012. Now I'd like to introduce the AAP Mountaineer Project, Matt Usher, who is the manager of CCS Engineering. Matt began his career with American Electric Power as a mechanical engineer in 1998. His primary area of expertise is air emissions control systems and equipment. Matt has a strong background in equipment and systems designed to control NOx, SOx, particulates, hazardous air pollutants, and other emissions from coal-fired power generation plants. In 2010, Matt was selected to be the engineering manager in AEP's New Generation and CCS Engineering group. Matt led a team at AEP that provided technical oversight of the front-end engineering design, or FEED, for the AEP and US Department of Energy initiative to engineer, construct, and operate a commercial-scale carbon capture and storage facility at AEP's Mountaineer plant in New Haven, West Virginia. Matt has a Bachelor of Science degree in Mechanical Engineering from the University of Kentucky, a Master's degree in Business Administration from Otterbein University, and is a licensed professional engineer in the state of Ohio. We'll endeavour to get through as many questions as possible in this session. Attendees are welcome to submit questions throughout the discussion, but please be aware that we may not be able to answer all of them today. We will aim, however, to answer all relevant questions which add to the discussion in the near future. Please type in any of your questions in the chat box that you'll find on your display. I'd like to hand over now to Matt Usher of AEP.
Thank you, Martin. Just getting everything squared away here on my computer screen. All right. Can everybody see the display with the Mountaineer Commercial Scale CCS project presentation? Martin, are you seeing that?
Yes, I can.
Okay, great. What I'm going to do is just give a project overview and summary of the front-end engineering and design activities that took place for the Mountaineer project. I'm going to talk through a lot of the technical details, realizing that we really only want to spend 25 minutes or so on the presentation so that we can open it up for questions. So I might go through some of the material a little bit quick. But I want to give Guy some time on the back end of the presentation to talk through some of the cost estimating and risk assessment that was done as part of this phase of the project. So without further ado, I'll just jump right in. First, just want to give an acknowledgement to the U.S. Department of Energy who sponsored the project. They had a 50% cost share on the project. And then all of the integrated project team members, including Alstom, Worley, Parsons Group, Battelle, We had a geological experts advisory team assembled for the project to help us with the storage aspect, and also the Global CCS Institute. This was a Department of Energy funded project, so we have to adhere to their rules as we go through the project. So legal disclaimer there that we had to put in. But what I'm going to do today, in the 25 minutes that we have, is just give you a brief overview of AEP and of the Mountaineer plant. I'm going to talk a little bit about the project from a very high level, just what our overall project objectives were, and then I'll give a brief introduction to the chilled ammonia process, which was the technology we were using. Then I'll talk through the feed technical objectives, the summary of the feed activities that took place, and what our deliverables were to get us to the level of accuracy that we had in the cost estimate. I'll go through some of the key feed studies and investigations that had to be completed up front to sort of set the design basis for the facility, and then I'll talk through what our final conclusions and key technical takeaways of the conceptual design were. Then I'm going to turn it over to Guy and let him discuss our estimating approach, the project cost estimate a little bit, some of the major risks and opportunities that we determined, and talk through some of our risk modeling that took place. AEP, we operate in 11 states. We have upwards of 5.2 million customers in those states. As you can see on this slide, and I won't go through it all in the interest of time, but our coal and transportation assets sort of tell the tale of where AEP's priority lies in its generating capacity. We have over 7,500 rail cars and over 2,800 barges in operation to move coal to our facilities. And you know, our coal handling capabilities, you know, we have a terminal with upwards of 20 million tons of capacity, and we consume nearly 76 million tons of coal per year. Our generation capacity is weighted 66% in coal, and you know, that was a definite driver to our initiative with carbon capture and storage. Was we want to look into technologies that will keep coal viable. Mountaineer plant is located in West Virginia, just southeast of the Ohio border. We're right on the border of the Ohio River, and about 30 minutes from Charleston. That's probably the biggest city that New Haven is close to. We're operated by Mountaineer plant's operated by Appalachian Power Company. It's a single 1,300 megawatt pulverized coal plant. It has an electrostatic precipitator, an SCR, a wet flue gas desulfurization system, and it also has SO3 mitigation, has a Trona system for SO3 mitigation. The primary fuel is bituminous coal. Mountaineer was a host site for Alstom's 20 megawatt product validation facility for chilled ammonia. There's 2 on-site CO2 injection wells that were used for that project, and that facility operated from 2009 to 2011. We captured upwards of more than 50,000 tons of CO2, and we stored nearly 40,000 tons of that CO2 on site. And we're currently in post-injection monitoring phase of that project. So we had already had some experience with chilled ammonia from the validation facility, and we wanted to make sure that we carried that into the commercial scale project. The purpose of the commercial scale project, again, was to advance the development of Alstom's chilled ammonia process technology and demonstrate CO2 capture and monitoring at a commercial scale. I already mentioned who the project participants were and where the project was located. We went through some preliminary cost estimating with DOE and some models that they developed, and determined that we were looking at a preliminary cost of approximately $668 million. The agreement had DOE picking up 50% of that cost share, AEP providing the other 50%. The technical objectives of the project are to capture 90% of the CO2 coming into the CCS facility and store 1.5 million metric tons of CO2 per year, and again, just to demonstrate the technology at the commercial scale. A quick overview of the chilled ammonia process. Basically 3 steps. You have flue gas cooling and cleaning, CO2 absorption, CO2 regeneration, or I should say reagent regeneration to release the CO2. But we bring the flue gas in from the outlet of our wet FGD. It's chilled in a direct contact cooler. The temperature is dropped. We do that with water, and then the cooled flue gas enters the CO2 absorber, where it is hit with a reagent of ammonium carbonate and bicarbonate. The reagent absorbs the CO2, and then we go to the regeneration step, where we add heat and pressure to release the CO2. The clean flue gas is then sent back to the unit's exhaust stack. It goes through various water wash and stripping steps to remove some of the residual ammonia from the process. That is where the byproduct of the chilled ammonia process is produced, the ammonium sulfate. And when the rich reagent enters the regenerator and the CO2 is then released, it's compressed and sent for storage, and the reagent is then sent back to the absorber. The technical objectives of the front-end engineering and design process for AEP was to complete a conceptual design basis, establish our process design parameters, determine what our balance of plant systems integration needed to be. We wanted to find a proper location and arrangement of equipment that satisfied the needs of the plant site and would also fit within the boundaries of the plant site. And then we had to develop an environmental impact statement to satisfy the National Environmental Policy Act, which is something that the U.S. government has started, that any major project such as this that we would enter into, we have to file an impact statement that is released to the public that sort of outlines what all the potential environmental impacts of such technology would be. So that was a key part of this phase of the project. Ultimately, the objective was to come out with a plus or minus 25% cost estimate. So we needed to get the engineering and design documents in place to support that. And then we wanted engineering to be in a position to freeze a design early in the detailed engineering phase, which would have kicked in October of this year. Some of the FEED activities and the key ones that we went through with both Alstom and Worley-Parsons was to define our site design conditions and criteria. Included everything from weather data, site characteristics of the plant, available water and other utilities on the site. AEP, we've been in the power generation business for over 100 years, so we've developed a quite voluminous set of design criteria for each engineering discipline. And since this was a commercial scale facility that by all rights could have been operated well beyond the evaluation period, we wanted to make sure that it was going to adhere to all of AEP's engineering and design criteria, as well as other state and federal codes and standards. We completed periodic site walkdowns with the plant to determine equipment locations and our steam ties and other BOP ties. And then we had what we called integrated engineering and design workshops for both the chilled ammonia process and the balance of plant, where we placed AEP engineers in the offices with Alstom engineers and with Worley-Parsons engineers to really dig into the design, look at the lessons learned from the validation facility, understand where we had gaps and where we could improve the design, and we completed those workshops in roughly an 8-week period, and we traveled to Germany. Alstom traveled to us here in the States, and it was quite an integrated and beneficial activity that we went through. At the end of the day, we had a chilled ammonia balance of plant design basis. We had material and energy balance and process flow diagrams around that design basis, and it was quite comprehensive set of deliverables. We completed a process hazards analysis in this phase. We utilized Worley-Parsons has a proprietary process that they go through called a HAZID, or a hazardous identification process. It's something that was new to AEP at this early in a project, but it really paid dividends. We sat down with both Alstom and Worley-Parsons. We sat down with AEP safety and health personnel. We sat down with Mountaineer plant personnel, and we sat down with construction personnel. And we really walked through this project from start to finish to identify what all of our potential hazards would be so that we could get those documented, get issues addressed, understand the issues that were going to be facing us in later phases of the project, and just try to identify that all up front. With this being a relatively new technology, obviously we had the 20 megawatt facility of Mountaineer, but we did not have any other CCS technologies or equipment or processes at any of our other facilities. Going through this hazardous identification process with the team was critical, and we've actually adopted this within our own internal processes here at AEP to ensure that as we go into major projects in the future that we complete this step. So this was a great lessons learned for us. We also did detailed constructability reviews early on, where we had participation from AEP construction as well as construction experts from Worley-Parsons and Alstom. We talked about things like modularization. There's a lot of large equipment on this technology, and so we felt like if we could bring it in as big a pieces as possible, it would save us on construction time and labor. We talked about various means of equipment delivery. With Mountaineer being right on the river, we had access to a quite large barge unloading facility that we could bring in equipment by barge. And then we just talked through some of the construction-related risks. Another beneficial activity during the FEED study was we did 3D model accessibility reviews. Alstom and Worley-Parsons put together a very detailed 3D model for us. And we used that model on a monthly basis to just walk through the facility, look at where we needed maintenance access, where we needed access and egress, and just to determine the overall walkability of the site. The deliverables from the FEED study, again, I touched on these earlier, but just to show you all the stuff that was put together. We put together detailed process flow diagrams. We had a suite of material and energy balance load condition. Because the chilled ammonia process is largely dependent on ambient conditions with its refrigeration system, we not only wanted to look at extreme summer case, but we also wanted to look at low ambient conditions where we could take advantage of free cooling and relieve the refrigeration system somewhat. So learning from the PVF, we learned that having a suite of energy balances that address a lot of these different operating conditions goes a long way in how you size equipment and how you build margin into your design. We put together detailed general arrangements of the site, P&IDs, electrical one lines. We even got down into the system descriptions and control philosophy. And then again, we had the 3D model that went down as low as pipe diameters of 2.5 inches and greater, which is pretty rare for a project this early. But we wanted to make sure, again, that we were putting together a very accurate estimate of what it would take. Some of our key studies and investigations that I'll go through. One was we needed to supply steam to the chilled ammonia process, and we did learn that we could do that with Mountaineer's existing steam turbine arrangement. With the steam capacity and the existing steam capacity in the Mountaineer turbine, we found an ideal location to take steam between the intermediate pressure turbine and the low pressure turbine, where we could supply steam to the chilled ammonia process at its required temperature and pressure, even as the Mountaineer unit followed load and would cycle up and down on load. So that was a big benefit for the team is to locate one steam extraction for the high pressure regeneration steam, or I should say the higher pressure regeneration steam is still a fairly low pressure stream. But we wanted to find one point where we could operate for a range of unit loads as opposed to multiple steam extractions that would potentially require significant changes to the turbine. So that was sort of our criteria going in, that we didn't want to alter the steam turbine at Mountaineer very much, if at all, for this process, because it's one of several 1,300 megawatt steam turbines on our fleet. We try to maintain common equipment on those units so that if they have an issue where they need repair or spare parts, we can keep a common supply for those turbines. So that was important to us. Condensate return from the cap, we realized that we could bring back that condensate to the Mountaineer feed water heating system, reclaim some of that energy as it came back in, and offset a portion of the chilled ammonia process energy demand. So that was another beneficial thing that came out of the design with Alstom. The plant had some concerns, however, bringing that condensate back into their feed water heating system, because it could well be contaminated if there's a leak in some of the process heat exchangers on the chilled ammonia process. They could bring back some contaminated condensate. To minimize that concern, we put in a condensate storage buffer tank that would be continuously monitored for contamination, to give the plant comfort that anything coming back into their existing system was safe. We did a detailed reagent and refrigerant study where we looked at potential reagents for the chilled ammonia process. We looked at upwards of 20 plus refrigerants. The PVF utilized an R410A, and we realized that with the inventories and whatnot required for the 235 scale, that just wasn't practical. So we did a pretty exhaustive study and determined that anhydrous ammonia was the adequate reagent, just because of its high concentration, allowed maintainability and control of molarity within the process. It had the least risk of any impurity additions. We looked at aqueous ammonia, but you're bringing in a lot of water when you do that, so that's water that you have to ultimately handle in the system. And then it had the lowest capital and operating costs of all the reagents that we compared. The refrigerant ammonia offers the lowest energy consumption and the highest efficiency out of all the refrigerants that we studied, with the lowest installed capital cost. And again, ammonia, it has minimal environmental impact with respect to its global warming potential, and that was why we were entering into this project to begin with. So we felt like we needed to keep that as a priority. The byproduct handling, as I said, from the water wash phase of the technology, you get a fairly concentrated stream of ammonium sulfate. We talked to some end users of that product that would use it as a fertilizer material, and they expressed that they would prefer to have that in around a 40% by weight solution. That played right into the chilled ammonia process, which we were getting a stream at around 15 to 25% by weight. So we included some equipment in the design to further concentrate that up and provide a 40% by weight ammonium sulfate solution that we could then resell, or in the case that we talked for phase one, we're basically just giving it away to avoid the cost of disposal. We did have Alstom's model runs of ammonium sulfate and what the constituents were estimated to be. We shared that with local agricultural officials, and they had some specifications for ammonium sulfate fertilizers, and we were well within what their specifications were for heavy metals and whatnot. So we were confident that this is a product that could be beneficially used from the process. We did a CO2 compression study. That report is going to be posted very shortly, or may already be posted on Global CCS Institute's website to explain the details of that. But basically, we thought going into the project that we were going to see maximum injection pressures into the well, upwards of 35 psi or 207 bar. The injection pressures as we operated the PVF we found were much lower than that, in the 1200 to 1500 psi range early in the life of the well. So we looked at conventional compression to an intermediate pressure, and then followed that up with variable speed pumping to allow us the flexibility of injecting at a pressure that would, at only the required pressure, and not compressing all the way up to what we believe the formation would handle or could handle at some period in the future, and wasting all that energy. We found that compression followed by pumping was optimal in that scenario. And that was a key takeaway from the project, and you'll see that show up again later in our key takeaway slide. Again, I said we developed some high-level system descriptions and control descriptions for the process. All control and monitoring associated with the chilled ammonia process and the injection wells was generally going to be controlled by Mountaineer's distributed control system, the DCS terminal at the plant. However, it would not be in the main unit control room. We had a dedicated CCS control room located near the chilled ammonia process facility, so that we could keep its operations sort of close coupled to the process. And there was no direct control of the Mountaineer unit in that CCS control room, which allowed, with some security regulations that were in place, it would have allowed us to circumvent a lot of the processes and procedures that would need to be in place if we were going to house that control room in the main plant's control room. So we avoided some of that additional capital and expense of going through the security issues there. The control room features, it was designed to be a continuously occupied control room with 2 operators and a supervisor. It included all the necessary displays for safe operation of both the capture and the storage system. We could monitor what was going on in the storage wells from that control room as well, and it was quite sophisticated. The conclusion of the feed, again, the conceptual design basis from our point of view was sound and poised for kickoff of the detailed design and engineering phase. We felt like the chilled ammonia process design would meet its stated objectives. We were confident that from the operation of the PVF that we carried over the pluses of that system, and we eliminated some of the minuses of that system. The scope of integration was practical and achievable from our standpoint. The parasitic load estimates were accurate and realistic. The design basis more than adequately supported a plus or minus 25% cost estimate, and I think as Guy gets into his portion of the presentation, you'll see that it was more probably a 10 to 15% accuracy in our cost estimate, just because we put so much rigor into our conceptual design documents. And then we felt like opportunities for improvement certainly existed and could be realized in the detailed design phase. Key takeaways, again, the overall conceptual design and integration into the Mountaineer generating station was a success. We felt like we had a conceptual design that would have worked at the plant, and that the plant operations could have successfully operated. One thing that we did learn was to keep your integration expectations practical. This is early technology, and trying to go in with a lot of expectations of how you can integrate to, save the overall energy and to reduce your overall energy demand. We felt like you need to keep that practical and within what the plant operations staff can handle. A unit of energy is not a unit of energy. You've got to realize at what value you value your heat and at what value you simply decide that you're better off just throwing it away because of the capital expense and the technical complexity that you introduce with integration. So we kept our integration expectations practical for this scale, and we feel like as the technology evolves in the future, much like flue gas desulfurization and other means of emissions control, that we will find where we can integrate and we will optimize where it makes most sense. It was a collaborative process from the get-go with Alstom and Worley Parsons, and that was extremely instrumental in identifying many of our technical risk factors up front. We kept the plant personnel involved and informed. I can't tell you how important it is to have your plant people if you're retrofitting a technology like this onto an existing plant. I can't tell you how important it is to have those folks involved. They know their plant inside and out. They know where they can handle integration of systems. They know where they can handle additional equipment, and having their input was extremely important. Selection of a steam source that minimizes extraction ties and eliminated turbine modifications. I went into this a little bit earlier, but that was sort of a goal for us. Again, was to keep the steam supplies as simple as practical and minimize the amount of work, additional work we would need to do to the 1,300 megawatt steam turbine. We based the experience at Mountaineer with their injection pressures below what our maximum target was. That was a big learning key for us. And we found that, it was going to be sufficient to inject CO2 at pressures well below that, and we could reduce the overall energy demand and allow ourselves some flexibility with the use of compression and pumping equipment. So I'm going to turn it over now to Guy and let him talk through our estimating approach a little bit and talk to you a little bit about the risks and opportunities that we found during our cost estimate phase. So without further ado, here's Guy.
Thanks very much, Matt. Very much appreciated. Just a quick introduction here. Guy Ceramelli is a project manager in the generation business unit of American Electric Power. He has 26 years of wide-ranging experience in the electric power industry, including past positions in engineering, environmental affairs, and governmental affairs. Guy's project management experience includes both new coal and gas-fired generation. His current responsibilities include, among others, serving as project manager for AEP's carbon capture storage project. He is a professional engineer and certified project manager professional. As project manager, his specialty area focus is project risk management. Welcome, Guy, and look forward to your discussion of the estimate approach.
Thank you, Martin, and thank you, Matt, for your discussion, basically setting up a lot of the inputs to the estimate that we'll discuss. Up in front of you is basically the approach. While it's noted that this is a plus or minus 25% cost estimate, in reality, this is a very tight estimate, and it's really an upper limit estimate that we're going to give you. We did a bottoms-up approach here where in working with Alstom and others, major equipment costs came in on budgetary quotes for over 95% of the equipment. The 3D model, as Matt mentioned, provided us a very detailed view of the system and included all piped down to 2.5 inches in diameter. Labor costs were based on Worley Parsons database, and this the estimate we came up aligned with multi-prime contracting strategy, where we would release civil site work first, followed by structural mechanical, and then later electrical work. We did apply escalation with respect to the project execution schedule. In terms of process and tools, as Matt mentioned earlier, it was a very good collaborative team effort involving Alstom, Worley Parsons, Battelle, and a number of folks here at AEP. We did utilize a detailed work breakdown structure for the estimate, which is a best practice in developing estimates and applying risk to those types of estimates. We applied our lessons from the product validation facility, and then we also applied an advanced estimate risk modeling technique in accordance with the American Association of Cost Engineers. The risk model was a combination of range estimating and Monte Carlo analysis. We focused in on areas of the cost estimate at the lowest level of the work breakdown structure where we would have an uncertainty or risk on the order of magnitude of about 0.5% of what we thought the total cost estimate would be. For example, if you're looking at an $800 million project, we would look for those uncertainties or risks in around the $4 million range. We did do a collective project team review, a red team review, meaning basically we put the people that developed the estimate in a room with other folks, their peers, challenged the estimate, and talked through any differences. It was a very good discussion. We spent over 5 days vetting this particular estimate. As a part of the scope of the estimate, and I want to underscore with the estimate we're going to show you, the big risks in this project are associated with the injection monitoring system, post-closure care. We are showing 2 injection wells for this particular project, 9 deep monitoring wells, 4 intermediate wells, and a characterization. And we drilled a characterization well. We drilled a characterization well in the upper yellow circle there that you see just off of the plant site proper. I can tell you, showing you this injection and monitoring system and the number of wells that we have here, there is a lot of uncertainty on whether we would be required to put in additional wells or if less wells could be used, as in the United States we have yet to have a permit application go through for this type of project. Just a quick picture showing you the drilling of the characterization well that we used for this particular project, and it's probably a little bit of a teaser slide here. I do show a core sample from our drilling. It shows vugs, as the geophysicists will tell you, vugs are something rare and unique and something you like to run into on a site. For those who have an interest in the reservoir and the formations here, we do encourage you to go to the CCS storage report. Well, back to the estimate. The figures I have in front of you, I want to underscore that, again, the cost uncertainty is on the storage side. I didn't put in the figures distinguishing capture and storage. We are encouraging our readers to go to the feed report when it's available to truly understand everything that we considered in this estimate and where all the uncertainties lie. We did come up with an overnight cost estimate of $825. We applied $71 million worth of escalation to the estimate to bring this project to $896 million. We also applied the risk model, identified all our 0.5% risk, and we came up with an upper limit risk-based contingency of $103 million. As an owner, AEP is assuming all the risk on this project and would have to cover the entire cost of the project short of our DOE cost share. That $999 figure represents everything all in. It's pretty much an upper limit number for us at this point in time. Phase 4 operations, we figured at $66 million. Total project costs, $1.065 billion. Again, this is a bottoms-up estimate based on 10 to 15% engineering and use of a 3D model. Quickly, I'm going to hit a couple risks here. We do encourage you to go to the detailed report. I can tell you escalation is a big issue for us. We had wide-ranging scenarios considering a double-dip recession and the possibility of hyperinflation with some of the commodities, some of the hyperinflation that we experienced here as recently as 3 and 4 years ago. So as economies recover in this time frame, we are worried about escalation, and there's a lot of variability there. I mentioned the underground injection control permit. It's an application first here in the United States, and there's significant risk around the cost of the number of storage monitoring wells we'd have to put in. Craft labor is another issue here for this particular project in the U.S. in general. The electric utility industry has a number of regulations being imposed on us at this point in time requiring considerable expenditures, and there's a possibility we could run into labor shortage. Scale-up risk is a possibility here on the capture side, but based on our operation of the PVF, we don't see a lot of risk in scale-up. The biggest risk in scale-up might be the long-term the long-term ability of the materials to hold up under potential corrosion. Opportunities, we see a lot of potential down the road in phase 2 detailed design to reduce costs. We see modularization as a way to save additional costs. We could apply AEP experience there. And Alstom's also performed a RAM study that showed us where we have significant savings in reducing spares and maintaining reliability of the facility going forward. We also believe we're significantly over-designed on structural steel. This next page, I show a slide that just gives you a relative ranking of the risks. You can see the biggest risk on this project will be the number of intermediate wells. There's a possibility we could be subject to a requirement to install an additional 10 intermediate wells at $4 million a well. Labor overtime is our second biggest risk, and then you'll see escalation volatility around materials, labor, and purchase services as other big risks. We have risk around installation of the deep wells and the injection wells in terms of just the inherent uncertainties around drilling and the costs you're exposed to. The two risks shown for support steel are actually opportunities for cost savings, but they're shown there relative to the other risk. This project will range all in everything, upper limit anywhere from $962 million to $1.065 billion. I want to remind the listeners that $66 million of that is attributed to the operations of the facility in phase 4 for just about 4 years. In summary, we'd like to say that the work completed in phase 1 really continues to support the commercial readiness of Alstom's chilled ammonia process technology at that intended scale. AEP and DOE have a real good understanding of the project's risks, capital costs, and the cost of expected O&M during phase 4. We believe this completed front-end engineering and design package provides a sound basis for completion of the project when conditions warrant its continuation for this particular project or a similar project elsewhere in the U.S. If you'd like to see learn more about AEP, we've put our web address in there. And I think we're at the point where we'll entertain Q&A. I'm going to hand back to Matt to handle most of the questions. And we may direct a few of the questions to myself and Indra, who's also in the room. Matt?
Okay, thank you very much, Guy. That's much appreciated. And we've had a number of questions coming in, and we've actually got a question here, which is a storage question. And before I introduce that particular question, I'd like to introduce Indra Bhattacharya, who is a geophysicist working in the generation business unit of AEP. He began his work with AEP in the summer of 2009, focusing primarily on the sequestration aspects of AEP's CCS project. He's been involved in the CO2 injection monitoring activities of the 20 megawatt CCS validation project and in the design, review and planning of the sequestration activities of the commercial scale project. Indra is a contributing member of 2 U.S. Department of Energy regional carbon sequestration partnerships, those being CCARB and MRCSP, as part of AEP's involvement in DOE's regional geologic characterization effort. Indra has a Bachelor and Master of Science degree in Geophysics from Indian Institute of Technology, Kharagpur, and a PhD from Ohio State University. The question for Indra today is from Robin Irons of E.ON. Has there been a report made public on the ongoing CO2 monitoring activities of the 40,000 tonnes of CO2 stored from the 20 megawatt pilot operation which preceded this feed?
Well, as a part of the UIC permit that we have, we are required to do an annual monitoring and reporting to West Virginia DEP. There is an ongoing monitoring that happened while we were injecting the CO2, and this report is due May every year. So we had already submitted one report May last year, and the next report is due May 2012. So I don't know if this is probably a public document, but I will have to verify it with our folks at our people to know that if this is actually a document which can be shared. But so all these monitoring activities are documented, and it is being recorded.
Thank you very much, Indra. We've got a question here. It'll be to Guy. It's from Justin Bala of Tanaska. Can you describe how were you able to generate accurate bulk material quantities and a 3D model without advanced status P&IDs?
We believe we did, based on the level of effort that we put in to the model and bringing the collaborative approach, bringing our construction folks into the discussion.
Okay. Again, thank you very much, Guy. This is a question that's actually from a number of different stakeholders. What is the status of the Mountaineer project, and what do you see as being the next steps?
Martin, this is Guy. I'll entertain that question. The Mountaineer project is officially in a suspended status right now, and that's principally due to the lack of federal climate change legislation here in the United States. Without that federal climate legislation, AEP is unable to receive recovery of the cost associated with the construction of this particular facility, and we'll keep it in that suspended state until policies here in the U.S. change and we have a mechanism for cost recovery.
Thanks, Guy. That's fairly clear. I've got a question. It's probably better to be addressed to Matt. It's from Eni Oko, a researcher at Cranfield University in the UK. His question is, what operating issues or challenges do you envisage when the CCS plant comes on in operation, particularly regarding operating it alongside the existing power plant?
Well, for this scale, Mountaineer's main unit was large enough at 1,300 megawatts that for the slipstream that would have fed this system, which was nominally around 260 megawatts was what the final design came to. We could operate this facility at 100% of its capacity for the entire normal operating range of the Mountaineer unit. So even as the Mountaineer unit would come down on load to follow customer demand, etc., the chilled ammonia process could stay at its full capacity. So that was an advantage of retrofitting the system onto an existing large unit. Now, we certainly, we're looking ahead at further scale up and what those impacts would be, and we found that, just maintaining the reagent molarity and handling water balance issues was probably the biggest challenge. That was a challenge that we had on the validation facility, was just managing the water balance around the system. You've got a large refrigeration system, large heat exchangers. So there was also some concern with materials of construction, and not having significant runtime on the PVF other than the 2 years that it operated. We wish we would have had more insight into how some of the materials of construction would have lasted, into the 5-10 year range. So I'd say from a high level, the biggest operating concern that we knew was there was water balance and materials of construction.
Thank you very much, Matt. Our last question, actually second last question. This is from Adam Dawson, and it's probably be directed either to Matt or to Guy. How much did the feed study cost, and how long did it take?
The feed study was about a 20-month effort. Yeah, it was roughly 20 months that was spent, and that included a lot of the administrative time leading up to actually getting started on the feed, but getting contracts in place and whatnot. And it was upwards of approximately a $30 million price tag, and that's everything. That was everybody's time and effort that was involved, from all aspects, from the storage and capture. That wasn't just capture, that was storage and capture. And we did a fair amount of geologic characterization as part of the feed study. We were actually drilling characterization wells and taking core samples, so that was a large part of that cost.
Okay. Again, thank you very much for that. And the last question of tonight is from Jeff Phillips of EPRI. This is probably best to be directed to Matt. The 3D model shows the capture plant is some distance from the stack. I assume that is because of available space. How much pressure drop does the long ductwork add?
Oh, I don't have my pressure drop numbers right in front of me. It was a considerable pressure drop just for the long duct run. I'll address the question this way. The area that's shown there was available. Mountaineer was in a unique position where it was originally sized for 2 units, so we had available space adjacent to the existing unit. However, it wouldn't necessarily, we would not necessarily have to return the flue gas from the chilled ammonia process back to the existing stack. That was a design decision that was made on AEP's behalf because we wanted to avoid some additional modeling from an environmental standpoint that would have had to have taken place had we introduced a new emissions point from the chilled ammonia process. There was considerable risk with of adding an emission source to Mountaineer, and it would have had to have gone through a lengthy permitting process to do that. We felt like it would have added too much time to the project, and we weren't about to take on that risk. So we returned flue gas back to the stack. Hindsight being 2020, I think we would allow ourselves enough time in a project to obtain the proper permitting and put an emissions source right at the chilled ammonia facility, so that we would not have to have all that additional ductwork returning back to the existing stack.
Thank you very much, Matt. And that leads us now to a point where we will be shortly closing down the webinar. I'd just like to thank Matt, to thank Guy, and to thank Indra for their valuable time in making the presentation and providing the update. I'd like to thank all listeners and attendees for participating and for the very, very valuable questions that have been brought to bear today. I'd just like to make a mention that the full feed study report will be published on the Global CCS Institute website very soon. I hope that the listeners found the activity valuable. We certainly welcome feedback on today's event as well as on future topics, our format, etc. Just like to remind everyone that we actually have recorded this webinar and we'll be posting it online shortly. There have been additional questions posed by online attendees. We will aim to answer all those relevant questions which will add to the discussion in the near future. And again, we'd like to wish everyone a good morning or a good afternoon or a good evening wherever it is in the world, and thank you for your attendance.